Okay, just to give you a big overview of where we are going to be talking all this week about just one idea. How do I find the largest and smallest values of a function on its domain? And that process is called optimization. So we're going to do that all this week. At the end of this week, we're going to have a test on our applications of derivatives, and that test is going to cover all of the graphing stuff that you did, like your project, and it's also going to cover the Newton's method and tangent line estimation and L'Hopital's rule that we did last week, uses of tangent lines, and then the optimization stuff that we do this week. So there it is. We're going to start with a definition that is going to look somewhat familiar, but not perfectly familiar. We're going to say that f of c is the absolute maximum of f of x if f of c is greater than or equal to f of x for all x in the domain of A. And likewise, f of c is the absolute minimum of f of x if f of c is less than or equal to f of x for all x in the domain. Now, what does this language remind you of? What does this remind you of? Where else have we defined? It looks like a local x, right? But there are two key differences. And the first is just the terminology, absolute instead of local. And corresponding to that is for all x in the domain. And to give you an idea of how these are similar and different, I want to consider the function f of x equals x squared on the interval -1 to 2. Everybody go ahead and sketch a graph of f. And of course, your graph should look just like this. -1, 2, 4, 1, just like that, right? Now let's answer some questions. What is the absolute maximum value of f of x? 4, that's right. And we would say that absolute x is located at x equals 2. What about the absolute minimum value? 0. Does this function have any local maxes or mins?
Local min.
So f of 0 is a local min. Does it have any local maxes? No, it doesn't. So notice that a local min could be, but does not have to be, an absolute min. And an absolute min could be, but does not have to be, a local. And an absolute max could be, but does not have to be, a local max as well. So the notions of local max and min absolute max and min are related notions, but they are not the same notion. Okay? Now, with that in mind, let's consider some different functions, their absolute maxes and mins, if they have them. What's the absolute max value of f? 5. What's the absolute minimum value of f? Also 5. Notice that a constant function will have its absolute max and min the same value. The converse is true as well. If the minimum value of f is equal to L, and the maximum value of f is equal to L, then f of x has to be equal to L for every x in the domain. That's an application of the squeeze theorem in a way, yeah?
Is there any chance that the function doesn't will either
Great question. Do all functions have absolute maxes and mins? That's great. So let's consider the function g of x equals 1 over x on the interval 0 to 1. How come I can't include 0?
You can, it's on that.
1 over 0 is not a number, right? Okay, so here comes my function with a nice vertical asymptote. What is the absolute minimum value of f?
one?
1. And it occurs at x equals 1. Question. What about the absolute maximum value? That's not a value. There is no absolute maximum value. If you give me any real number whatsoever and say, oh, that's the largest value, I can find an x close enough to 0 so that f of x is bigger than that value. We say that f is unbounded. So f has no absolute maximum. And that's because it has an asymptotic discontinuity in its domain. Actually, not even in its domain, but adjoining its domain, or a point that is on the boundary of its domain. Let's consider another situation that's kind of similar. Let's consider h of x equals x squared on the interval negative 1 to 2. Now, this is subtly different from the one that we had previously. Our example over here was f of x equals x squared on the closed interval, negative 1 to 2. Now we're considering h of x equals x squared on the open interval, negative 1 to 2. And when I graph h of x, you can see that it has a minimum value, the absolute minimum of h of x, is 0, but it has no absolute maximum value. Why not? Because it has a least upper bound of 4, but it never achieves that least upper bound. I can let x equal 1.9, 1.99, 1.99999, but x equals 2 is not in the domain. You see it?
So then, so it wouldn't be 1.999 whatever. It would-
How many whatevers would you go? See, there's your problem. Yep. Yes, sir. That's a great question. Do you have to draw the graph to find the absolute max? Turns out the answer is no, you don't. And today we're going to get a couple of theorems that will help us to find, first of all, to have confidence that we do have an absolute max, and second of all, to find it. Great question. Okay, so what we observe is that not every function has an absolute max or an absolute min on its domain. And so we wonder what conditions guarantee that a function does. And that leads us to our first theorem for the day, the extreme value theorem. If f of x is continuous on the closed and bounded interval a to b, then f of x is guaranteed to have an absolute max and an absolute min on the interval a to b. Now, in Calc 2, we actually proved this theorem, but here I just want to appeal to your intuition that if I start at x equals a, and I draw any continuous curve whatsoever out to x equals b, then because my curve is continuous, it must achieve its least upper bound here, and it must achieve its greatest lower bound right there. So that it has to have at least one, maybe more than one, point where it achieves its absolute max and its absolute min. Yes?
For its absolute max.
And. There. Okay. Now, we have an idea of what functions have absolute maxes. And the answer is continuous functions on closed bounded intervals. Notice that there are two conditions. It has to be continuous, and it has to be continuous on a closed and bounded interval. If I don't meet those conditions, there is no guarantee. So for example, if f of x is not continuous on a to b, for example, this function has a jump discontinuity right here at x equals c, then notice that f of x doesn't have an absolute max. So continuity is required. But it's also necessary for the interval that we're talking about to be closed and bounded. In other words, it has to have an endpoint A and it has to have an endpoint B, and those endpoints must be included in the domain. So for example, if I have f of x equals x on negative infinity to infinity, it's pretty clear that f of x is continuous, but it also is pretty clear that it doesn't have a max. And that's because my interval is not bounded. And we saw earlier that our h of x was continuous on a bounded but open interval, and it didn't have an absolute max either. So continuity on a closed bounded interval is necessary in order to guarantee the max and min. Without it, I might accidentally have a max or min, but there's no guarantee. Next question, how do I find it? And that's really what we're going to spend the next 4 days doing, is finding the absolute max. And we're going to have two methods, and I'm going to teach you just one of them today. By extending Fermat's theorem. Do you guys remember Fermat's theorem? Maybe you remember it like this. Local extrema only occur at critical points. That's it. That's Fermat's theorem. Now, to extend Fermat's theorem to consider now absolute extrema, I want to take a look at two possible ways that you can have an absolute extreme value. First of all, consider consider this function right here, I think we can see from the graph that f of a is the absolute min. And I think we can also agree from the graph that f of c is the absolute max. Now, if we take a look at f of a, let's look at f of c first. If you take a look at f of c, you can see it's the absolute max, but you can also see that it's a local max. And it's a local max because it is found in the interior of the interval a to b. In other words, any absolute max or min that is in the interior is also a local max or min, which means it must occur at a critical point. What's the only other possibility? When it's not in the interior, it has to be at an endpoint. And that's the case with f of a. F of a is not a local min, but that's only because it's on an endpoint of the interval. And so if we take these observations and put them together, we would reason like this. We'll call this the critical point endpoint theorem. Absolute extreme only occur at critical points or endpoints. Yes, that's correct. So not all endpoints are absolute extrema. But absolute extrema can only occur at critical points or endpoints. Good observation.
So I'll call that critical point. Those should be local.
That's right. If you have an absolute max that is occurring in the interior, it will be a local max as well.
Always.
Has to be. Because remember what a local max is. It's the max in its neighborhood. So if there is a neighborhood within it. Okay? Now this theorem leads us directly to a method for finding absolute maxes and mins that we call the critical point endpoint method. And the critical point endpoint method doesn't require a graph, which is really nice. That was Jason's concern. He was worried that we'd have to sketch these things before we could find the maxes and mins, and we don't. What we're going to do is we're going to identify candidates. And our possible candidates are the critical points of F and the endpoints of our closed bounded interval. Notice that I'm assuming there is a closed bounded interval here. So we have to have a domain that is a closed bounded interval for this to work. Then, having identified the candidates, really simple, we're going to evaluate F at each candidate. And the biggest one is the max. The smallest is the min. That's it. Now notice that this assumes continuity on a closed bounded interval. If my function is not continuous on a closed bounded interval, then I'm going to have to do something else. So then we're not going to worry about that today. We're not even going to worry about that until the end of class 1. Okay? Now let's actually apply that in this situation. Find the absolute max of f of x equals x cubed minus x on the interval -1 to 2. Let's make it 3x for convenience sake. Okay? And you know what? Since we're doing this, let's find the absolute min at the same time. Let's make this a tuple, so we get a complete range here. Alright? So, our first step is going to be to identify the candidates. And the first two candidates we identify are the endpoints of our domain. Automatic. These guys get a bye. Then, for our other candidates, we are going to get critical points. So we need f prime. Set that equal to 0. Factor at will. And x equals 1 or -1 are the solutions. Notice that one of those has already been taken care of in my domain. Represented again, but I have a third candidate now, x equals 1, which are my candidates. This is my whole list of candidates. And now it's a simple matter of evaluating f of -1 is equal to -1 cubed minus 3 times -1, which is +2. F of 2 is 2 cubed is 8 minus 6 times 2, which is also equal to 2. And f of 1 is equal to 1 cubed minus 3, which is -2. Therefore, this is the absolute max value, which is 2. Please notice that the max value is a y value. It is not the x value where it is located. Right? So don't tell me x equals -1 is a max. That doesn't make any sense. The max value is the y value, the maximum value of the function. And then the minimum value is -2. Yes, sir.
But 2 is not local max.
Correct. That's right. This is an absolute max, this is an absolute minimum. And if we were to graph this, at x equals -1, we have this guy, and then my function comes down, that comes back up like so. Concave up like so. So we have an absolute max, but no local max. We have an absolute min, which is a local min. Does that process make sense?
Oh, this one is local max.
What's that?
Oh, local max.
There is no local max there. Functions don't have to have local max.
So what about x equals to -1?
Because that's at an endpoint right here,
It's also a critical point.
yes, that's right. But it's not local because there is no open interval containing x equals -1 for my function in the domain. So notice that to be a local max does not require that, excuse me, not every critical point is a local maximum.
It's assumption.
Right, yeah, exactly.
Where we set up the domain and
Right.
change some.
Yes, then you would actually have a local min there, and x equals near. And then they are doing anything -1 plus delta. Minus delta. Okay, now, how does this actually work out with regard to word problems? Because tonight, your homework consists of 5 word problems. And so what has to happen is you have to take those word problems and translate them into an equation, establish the domain, and apply the critical point endpoint method. So, let's practice doing that. The rest of our time, we're going to practice translate. If you have your book, take a look at page 226. Number 1A. Now on page 226, we are told that the sum of 2 non-negative numbers is 20. And they ask us to find the numbers if, and then they give us 2 different conditions. This problem is a little bit confusingly worded. What they're asking are really 2 different problems. They should have done this as A and B, but they didn't. If the sum, excuse me, the product of the numbers is as large as possible. And then in the second question, they ask, find the numbers if the product of the numbers is as small as possible. Now the math, the actual calculus on this is really, really easy. We're going to focus our attention on the translation from English into math. And you want to go through and translate each sentence, paying attention to every word as a detail. So let's start with this first sentence. The sum of 2 non-negative numbers is 20. How can we translate this into math? First of all, what does sum mean? Addition, that's right. And what am I adding? Non-negative numbers, right? What's the difference between positive and non-negative? Non-negative numbers can be 0, positive numbers cannot, right? And that's going to matter for our domain. Okay? So, do I know what these numbers are? No. So therefore, I, the problem solver, need to call them something. Clara, what would you like to call our 2 numbers? You can't give them specific values because you don't know that they are 0 and 20. No. So you need to call them something. Jason, what would you like to call them? No? Okay. X is a good choice?
X and 10 minus X.
And 20 minus X. Ooh, I like that. Yeah. 2 options we could have picked. Option 1 is to use one variable. If we do that, then our 2 numbers are X and 20 minus X. Option 2, which I prefer a little bit, is to use 2 variables because I've got 2 numbers, and then I'm going to call them X and Y. And they are constrained by the fact that their sum is 20. The sum is 20. You see how the English corresponds word for word way, I'm going to end up with the same equation in the end. Okay. Now, the next thing is I need to deal with the phrase non-negative. This is telling me something about the domain of my problem. Specifically, it is telling me that x is greater than or equal to 0. But actually, it's telling me something a little bit more. Yes, because if x must be greater than or equal to 0, 20 minus x has to be greater than or equal to 0 also, which means that x cannot be larger than 20. So this is the closed and bounded domain for my problem. Now I have finally disposed of my first sentence. Now we're supposed to find the numbers, find x and y, or find x and 20 minus x, if the product is as large as possible. Let's look at this phrase right here, because this is new for us. Is as large as possible means is an absolute max. You see what I mean? This is code for is an absolute max. And what I want to be an absolute max is the product of those numbers. And so what does product mean? Multiplication, that's right. So I'm going to do my product of those numbers as, and if I'm working with option number 1, my product is going to be x is 20 minus x. If I'm doing option number 2, my product will be x times y, but since x plus y is 20, that means that y is 20 minus x, so that my product is still x times 20 minus x. So whether you do option 1 or option 2, you end up with the same equation regardless. And of course, the domain for this formula is all x values between 0 and 20. Are we good? Now we have put this problem into a form that we know how to deal with. We have a function of one variable with a domain. Our function is continuous on the closed and bounded domain, and so we can appeal to our critical point and point method. We can identify the critical points, and we can identify the endpoints. So we're going to list them, and I just recommend writing the word candidates right here. And our first candidates are going to be the endpoints of our domain. X equals 0 and x equals 20. To get other candidates, I need the derivative. So p prime is going to be the derivative of, and it makes sense here to do a little bit of algebra, and to write p as 20x minus x squared. And set that derivative equal to 0, so that I get a single critical point, which is x equals 10. That is my third candidate right here. Now I can evaluate the product. The product when x is equal to 0 is 0 times 20, which is? The product when x equals 20 is 20 times 0. Did you notice the symmetry in that problem? If one number is 0, the other is 20, right? And then the product at 10 is 10 times 10, which is 100. So we have the max when, now we need to make sure we answer the question. What question did they ask? Did they ask for the maximum product? No, they asked for the two numbers. Go back and check the exact wording of your question here. find the numbers. So we need to make sure that we answer that question. And if x is 10, then y must be 10 also. What about here? Well, we have a min. But we have a min at two different points, or do we? If x is 0, what is y? No.
Oh.
Y is 20 minus x, right? But if x is 20, what is y? It's the same two numbers, I just switched their labels. It's the same two numbers, 0 and 20, that minimize. All I did was to change the labels on it. Yes, sir.
But F of X is 0 first.
When you say F, do you mean P?
Oh, P of X.
Yeah. P of 0 is 0. That's right. How good? Okay, good. I want to consider a second problem. Number 6. A rectangle has its base on the x-axis. And two vertices on the parabola y equals 12 minus x squared. What is the largest area the rectangle can have? And what are its dimensions? Okay. Now let's walk through here and translate this. Our goal is to get a function with a domain so that we can use the critical point endpoint method. Does that make sense? And in particular, I can go straight to the function I'm trying to find by looking for something, some language that has to do with maximum. What language do I see here that says maximum? Largest, that's right. So I'm looking for the largest area. That tells me the function I'm looking for. I'm looking for an area function. Okay? Now let's start translating. We have a rectangle with its base on the x-axis. Okay? So, I'm going to start with drawing myself a rectangle whose base, this is the base of the rectangle, is on the x-axis. And it has two vertices on the parabola y equals 12 minus x squared. Now, the vertices are these four corners right here. And it seems pretty clear that if I want the parabola to, if I want the rectangle to have maximum area, then I want the parabola to go like that. I'm not sure this is a well-expressed problem because I can imagine drawing a rectangle with two vertices here and going out to infinity. Right? This actually satisfies the conditions of the problem as stated. I don't think that was their intent. I think the problem was poorly worded. What they really meant to say is that the rectangle is inscribed within the parabola and the x-axis. So we're going to interpret their question in a reasonable way. Because if we interpreted it my way, even though it's consistent with the words, there would be no solution to that problem because I can make that rectangle as tall as I want. What is the largest area the rectangle can have, and what are its dimensions? Okay, so I want an area function here, but I don't seem to have a whole lot to go on. And what's missing is that I have not supplied coordinates yet for these four vertices. Now, I don't know the value of this vertex, so I'm going to need to call it something. And I'm going to call it x because it lives on the x-axis. So if I call the coordinates of this point x, comma 0, then every other point on the rectangle is automatically taken care of, because this point also has to have an x-coordinate x. Yes. And it must also live on the parabola so that its y-coordinate has to be 12 minus x squared. This is our key move, so I want to focus on it very carefully, because the rectangle has to intersect the parabola, therefore the y-coordinate has to be the y-coordinate of the parabola, which is 12 minus x squared, because that is the equation for the parabola. Does that idea make sense? We're going to go ahead and label these other ones here. This parabola is symmetric about the y-axis. It's an even function. And therefore, I can immediately label this point as negative x, comma 12 minus x squared. And I can label this point as x, comma 0. Excuse me, negative x, comma 0. It's the labeling of the points that is really the magic thing that makes this problem work. Once you've got the points labeled, then we can go through and start measuring distances. And once we've measured distances, the problem will be easy. Are we good so far with the full points? Okay. That takes care of our first sentence. We've captured all of this. But we do need a domain. And the domain is going to be found by considering the skinniest and the widest that our rectangle could be, and still be inscribed. If it is the skinniest, then x will be 0. If it is the widest, then our x-coordinate is going to intersect right here. What is the x-coordinate right there?
2.
Yeah, it's root 12. Which you simplified very nicely as 2 root 3's. Let's finish this up. We're almost done. So our domain is going to be x's between 0 and root 12. Now, what about the second sentence? What is the largest area? Well, this is a simple shape. It's a rectangle. What's the area of any rectangle? Base times height. The only tricky thing is the base of this rectangle is 2x. Why? This coordinate is x, that coordinate is negative x, x minus negative x is 2x. So the area is the base 2x times the height of the rectangle, which is the y-coordinate. That is 12 minus x squared. And now I have a function with a domain. I can very quickly do the critical point endpoint thing. My candidates 0, x equals 12, right, 10 points. And I can simplify the area and take its derivative. dA dx equals 4 minus 6x squared. And I get x equals 2 or negative 2. X equals negative 2 is outside of the domain. Now I evaluate each of my critical points and endpoints. And when x is equal to 0, the area is 0. And that corresponds to a skinny rectangle with no width. And when x is equal to root 12, the area again is 0. And that corresponds to a rectangle that has no height to it. But when x is equal to 2, my area of 2 is equal to 4 times 8, which is 32. This is my max area. And the dimensions of the rectangle are the length and the width. And the dimensions are 2x and 12 minus x squared. And we're done. Yes, sir.
Where do you root?
I got root 12 by asking where does this parabola hit the axis when 12 minus x squared equals 0. So x must be root 12. Or negative root 12.
Oh, so I guess that's
Yeah, yeah. The area is 32. So the dimensions are 4 by 8.